Hi everyone, how are you guys doing? Hope everyone is doing well. And yeah. Alright, so I'm just gonna jump right into it. Last time, what we managed to do is have an enemy or a player that basically moved in the world, right? Like so. It was easy enough, not that difficult. And we talked about how we can render um, parts of the image, so parts of our sprite sheet, rather than the entire sprite sheet, which is extremely useful. Right? That was our sprite sheet, and we kind of rendered just the first index in here. All right. So the next part that I would like to do is be able to create an enemy. Able to open. All right, cool. So I want to be able to create an enemy and detect collision between both the player and the enemy. Before I move on, I want to change the width of my screen to 9220 by 1080 because 1800 by 800 by 600 is kind of small, way too small. All right, that's much better. All right, so let's do that. So the first thing we need to do, and one thing I want to talk about is notice like all of this code, the creation of my variables, the loading part, setting the texture, that's all being done once, right? It's not in the game loop, that's outside the game loop. And you want to keep it outside the game loop because you don't want to do it over and over and over. You only essentially want to do it once. All right. So the next part that I would like to do is load an enemy, right? So what I'm going to do is I'm essentially going to copy this entire code. Actually, I'm just going to type it. All right, so I'm going to create a texture. So SF texture. And call it enemy texture. Now, the enemy texture and the player texture are essentially going to be the same thing, right? They're going to both have the same texture. So technically, I could use the same variable if I wanted to, but I'm going to assume that they're different. They're different. The enemy and the player are different, and so I am not. I'm just going to create a new variable for them. So I'm going to duplicate this folder. I'm going to call this skeleton. All right. Obviously skeleton is wrong. The skeleton is I think that's how you spell skeleton. Google, can you help me? Thank you very much. Hey, look at me. Spelling skills. Hell yeah. All right, so I got my skeleton. Oh, it's wrong. Well, there's a Fagarni. Never mind. All right, so skeleton, which has a texture, which has the sprite sheet, right? All right, so I'm gonna create my sprite now. So SF sprite, which is gonna be my enemy sprite. All right, and then I'm gonna do the same thing. I'm gonna load my sprite. So I'm gonna say if enemy texture dot load from file, and then I'm gonna set the path. The path is gonna be the same thing, so I'm just gonna copy this, paste it here. The only difference is this is gonna be called the skeleton. And if it's correct, I'm gonna copy this part. So I'm gonna say enemy image loaded. And this is going to be set to the enemy sprite. This is going to be set to the enemy texture. And the same thing. I'm gonna, you know what? I'm gonna render a different part of the sprite. So I'm gonna render the front. So this one. So this be 0, 1, 2. So 2 down on the y-axis, right? And so enemy sprite, and that should be that. I'm gonna have an else statement also. So else enemy enemy image, or it's going to be called skeleton. Actually, just rename this to skeleton. Skeleton. Skeleton texture, skeleton sprite, skeleton, 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 skeleton. By the way, if you don't know how I did that, how I kind of selected both lines and I kind of edited them, you can make a nice square. So for example, this is really cool. So if I go here, paste this, and then paste this, and let's say I want to change the skeleton, so I can highlight all the skeletons, and I can type, for example, enemy, right? Enemy like that, which is really cool. The way you do that is if you click Alt and Shift. So I'm clicking Alt and Shift. I'm holding Alt and Shift right now, and then I click with my left mouse button, and I can draw a kind of a rectangle. I can select the highlights that I want, or the words that I want to change. I can change them, and I can type in multiple lines, right? Which is kind of cool, right? It's something you can do. All right, so going back, controlling Z off this. So skeleton, sprite, skeleton, skeleton, skeleton. I'm gonna say skeleton image loaded. That's gonna be texture. Skeleton texture loaded. That sounds a little bit better. Player texture loaded. Player texture sounds a little bit better. That's all. All right. And so I'm gonna split this code a little bit. So I'm gonna have one more of these, right? And instead of float, I'm gonna say skeleton. All right. Gonna have one more for the player. Gonna be player and player over here. Maybe cut all the keys down like that. Why won't you select all of this? Okay. Copy this. Do that. A little bit of organization, that's all. Now, this code looks messy, right? Everything right now is in one source file, and I understand that. For more experienced programmers, they might look at this and be like, what is he doing? What the fuck is he doing? Right? Which is fine. I just wanna take baby steps, right? I don't wanna jump into anything yet. Anything more complex, right? So it's kind of cool. So this is like the player section. This is the skeleton section, and all of this falls under load, right? Which is kind of cool. A little bit organized. All right. So now, we go here. So I got my skeleton texture, the sprite. I checked. I'm checking if I can load. If this was loaded, if it was loaded, I say it was loaded. I set the texture. I set the index that I want. I set the rectangle. I set my scale. Right, and I say, hey, skeleton failed to load, which is fine. Right, now it's time to render it. Now, one thing that's very important that you should keep in mind is that the draw order matters. If you draw the player and then you draw the skeleton, right, that means the player will be under the skeleton. So I'll show you. So if I move, right, so this is my player, right? If I move my skeleton here, you can see that my player is under the skeleton because the order of the drawing matters. Whatever you draw first is going to be the first thing that's going to be drawn. And then whatever you draw next is going to be on top of that. So I'm drawing the skeleton, the enemy skeleton, on top of my player. Right? You can see how this is behind that. And if I want to switch the order, all I have to do is switch the order like that. Right? Restart my game. And now the player will be on top of my skeleton. I mean, both of them are skeletons, but yeah. You can see how the player now is on top of my skeleton. Right? So the draw order matters very much. All right. Now, one thing I want to do is be able to, I want to move my skeleton. Right now, my skeleton position is set at 0, 0. So I would like to move the skeleton position somewhere else. So in here, I'm going to say set position. And again, set position just sets my position for my skeleton. And it's a function, it takes a vector to f, and I can specify the position. I'm going to say it's at 400 pixels to the right and 100 pixels down. So if I press play, my skeleton should be, yeah, somewhere here. You can see that I'm drawing and it's working fine, which is kind of cool. All right, so the next part that I would like to do is be able to shoot bullets, right? For now, I'm gonna say that I have a gun, or the gameplay might not end up being like that. I mean, in the actual game later on, while we're developing it, the player might have a gun or a crossbow. I'm not sure, but he's gonna have some sort of projectile weapon that can shoot in a certain direction, right? Which would be nice, which would be cool. So let's kind of implement that right now. Okay. So this file is gonna get pretty big, right? It's gonna be a little bit messy, but it's kind of intentional because I wanna show you kind of, again, I'm gonna show you the not so good way of doing things and then how we can improve it later on, right? All right. So what is the idea of shooting bullets? How are we gonna do that, right? So if I go to where we were doing our thing, was it here? Yeah. Okay. Let's kind of go to a new section over here. Get my tablet out. That's okay. All right. So how am I gonna do this? Well, if you think about it, if this is your screen, right, and your player is over here, right? What you want to do, first of all, is, and let's say the enemy is over here. So this is the enemy. Actually, the player should be white. So I'm gonna make the player white, the enemy red. Okay, I'm a bullet screen. So essentially, imagine this is my mouse. What you see right now, like my cursor right now, is my mouse. And so what I want to do is be able to point my mouse anywhere on the screen. I have my mouse moving on the screen. And I would like to be able to shoot projectile in the direction of my mouse. So if my mouse is sitting over here and I click with my mouse, I'm gonna spawn bullets in the player position and move in this certain direction. Right? That's kind of the idea. Now, the question is, how are we gonna... The first problem we want to tackle is how do we spawn things? Like, how are we gonna do that? Because think about it, every single bullet technically is gonna be a sprite, right? Either a sprite or a rectangle shape. And so if we define one variable, so if I say there's one variable called bullet, which is a sprite or rectangle shape, I can move it in any direction I want, which is fine. But then how can we make more? Like, how can we make more variables? Each variable holds a single sprite. How do we do that? Well, we can create another variable. So we can call this bullet1. I can make another variable here called bullet2. Then I can make another variable. And I can make like 100 variables under each other. But again, that's an issue because now we're limited to 100 bullets, right? We can only shoot and move 100 bullets, which is a problem. So we can say all 100 bullets are where the player is. So they're behind the player, they're under the player. So the rendering order will be draw the bullet and then draw the player on top of the bullet, right? And so the bullets will be in the position of the player. And if I click my mouse, I'm gonna move the bullet from under the player in a certain direction. But again, I'm only limited to 100 bullets if I create 100 variables manually. And that's a problem and an issue, and the code looks disgusting and ugly because I'm creating 100 bullets manually. Like literally, I say SF sprite and I call it bullet 1, right? And then bullet 2, and then bullet 3, and so on and so forth. And so that's really ugly. It's not clean. And it's not the way of doing it. So what can we do instead? Can we make this a little bit better? Well, yeah, we can. Luckily, C++ has a concept of a list. So what we can do, we can make a list of bullets. In that list, I can add a bullet. If I want to spawn a bullet, I add a bullet to that list, and I move that bullet in a certain direction. And so every time I click my mouse button, right, I add a bullet here, and I move my bullet in a certain direction. So this way, my list will create a variable for every single bullet, which is cool. So I just have a single line of code rather than 100 lines of code. I just have a single line of code. And so I shoot a bullet, or I add a bullet to this list. I add a bullet variable to this list, or a sprite variable. It's actually, it's a bullet of type sprite. I add it to this list anytime I click my mouse. And then I update the bullet position to move in a certain direction. So that's essentially the idea. So if I go through this, if I Control-Z off this, and I go through this again, the first thing I need to do is create the list. So list, all right? I'm gonna have kind of weird brackets like this. Inside this list, I'm gonna have the data type. What data type is inside this list? Well, it's gonna be SF sprite. So basically, I'm saying that this list holds multiple variables, and all these variables in this list will have a data type of SF sprite. So this list will hold an SF sprite. Now I need to give my list a name. In this case, I'm going to name my list bullets. Not a single bullet, but multiple bullets, right? So now I've created, so this is very similar to doing this. So remember when we do here, so SF sprite, right? And here it's going to be a bullet. So this section, what color? This section, right, is pretty much the same. In here, I'm creating a variable called bullet. In here, I'm creating a variable called bullets. So this is a single bullet. This is multiple bullets. The data type of my bullet is an SF sprite. A single SF sprite. The data type of my bullets, all of my bullets, is a list of SF sprites. So this bullets, it doesn't contain just a single bullet, it's going to contain an entire list, right? And so this is going to be my list. And the cool thing is that we can add multiple bullets in that list. So what I can do, essentially the idea here is that I can do this. I can say bullets dot add SF sprite, right? So I'm adding an SF sprite to this list. So what this will do is create a new entry. So at the very beginning, this list is empty. So it's going to add here an SF sprite. And then if I call this line again, right, I add another SF sprite. And then if I call this line again, I add another SF sprite. So now I have 3 SF sprites in this list. Okay, so that's how I add things to my bullet. Well, this is a little bit different. This is not C++, by the way. Like, this code is not technically C++. Well, not technically. It is literally not C++. But just to make things a little bit easier for you, I'm doing add, right? So bullets is this list. So in memory, this is bullets, right? This entire list refers to bullets, right? The entire list is bullets. Whenever bullets has a function, or my list, this list has a function called add. This add function, I can add a new sprite to it. So anytime I say bullets, which is my list, add a sprite, it will go and add a new sprite. And then call it and add new sprite, and again and again. So now the question. I can access this entire list by just calling this variable, right? This variable bullets, I can just refer to this variable and I have access to the entire list of bullets. The question is, how can I have access to a single bullet? How can I access this bullet or this bullet? Because what I need to do, it's nice that I have access to all the bullets, but I would like to access a single bullet and kind of move it or do something with it. So how can I access a single bullet from this list? Well, luckily, every single bullet, right? Every single item in my list, this is item number 1, item number 2, item number 3. Every single item here has something called an index. And we looked at indices before and what an index is before, right? We created a variable here called int x index, and we mentioned how index, I can use it to get a specific image in my 2D images, right? You can think of these 2D images as, again, a list. It's just a 2-dimensional list with x and y coordinates. This is a 1-dimensional list. It just goes down. So what I can do is I can access every single sprite in here with an index number. And we mentioned before that an index number starts always from 0. Whenever we're dealing with indices and indexes, we start from 0. So to access this sprite, we say, I would like bullets at index 0. I'd like bullets at index 1. I'd like bullets at index 2. So 0 is the first bullet. 1 is the second bullet. 2 is the third bullet. We always count from 0. We always start from the value 0. All right? This might be a little bit confusing because when I say I want the first element is not 1. The first element is 0. The second element is 1. And the third element is 3. All right, if this is a little bit confusing, there's a nice way to kind of remember this. There's a small formula that's called n minus 1. N stands for which item you want in your list, right? So in here, in this case, I would like the first bullet in my list, like the first bullet. So what I do is I type, I want the first bullet. So the first bullet is 1. So let's do this in here. I'd like the first bullet, and the first bullet is 1. Okay? To find the index, I use this formula. So the index of the first bullet is 1 minus 1, which is 0. So now the first index, the first element is index 0. The first element in my list is index 0. What if I want the second bullet? So I want this second bullet. So again, I do the same. I say that I want the second bullet. So the second bullet is number 2 because it's the second bullet. 2 minus 1 will get me 1. So now I have the index of the second bullet. The index of my second bullet is 1, which is over here. What if I want the third index? The same thing. I want the third index. I want the third, so that's number 3. 3 minus 1 equal to 2. So this will be the index of my third bullet. All right? So always remember that. If you ever were wondering, okay, I want the 100th bullet, right? I want the 100th bullet. Well, to get the index of the 100th bullet, it's just n minus 1. 100 minus 1 equal to 99. So the index of the 100th bullet is at 99, right? So that's kind of a nice way to remember this. All right, cool. So I have my list of bullets. I can access every single element in my list of bullets by numbers, right? So number 0 is the first, number 1 is the second, number 2 is the third, right? Okay. So how does this actually work? How can I access it? How, like we said that's 0, 1, 2, but how can we, what's the code? What does it look like? Well, it's pretty simple. Essentially what you do, let me erase this. Essentially what you do, the first thing you do is type the name of the list, right? I named it, this is my variable called bullets. So I named my list bullets, right? So now how can I access the first element? Well, what you do is you add these brackets, right? These brackets, basically what they mean is they can access as any element from that list. So if you say bullets at index 0 dot set position, right? I can do that. Now this function set position, right? We said that every sprite, like if we look at our code here, every single sprite, right? This is skeleton sprite of data type sprite. So my skeleton sprite has a function called set position. So what if I want to set the position of the first bullet? So I access the list of bullets. I go to its index, and we said it's index 0. The first one is index 0 because n minus 1, 1 minus 1 is equal to 0. That's the first bullet. So I go to the list. I get the first index, and from there I can call set position normally as if I would be talking to that sprite, which I am. I'm actually not technically. I'm actually talking to the first sprite. So I have access to set position, get position, set scale, get scale, all the functions that you normally have for a sprite, you get here because it's actually a sprite. You are communicating with a sprite. Now, one more thing that's very important to note is that if you forget to add this and just do bullets dot set position, that's a problem. That's an error because bullets itself is not a sprite. Bullets does not have the function set position because bullets is a list. However, bullets at index 0, you're communicating now with the sprite itself. You're communicating with this element. While if you just say bullets without this, you're now communicating with the list, not the elements, right? So just keep that in mind and keep that clear. All right, so I'm going to my list. I'm accessing the first element, which is over here, and then I'm setting its position. What if I want to set the position of my second element? Well, 2 minus 1 is 1, right? So that's the first index number 1. The second element is index number 1. So I do this. And now I'm communicating with this sprite. And so on and so forth, right? So that's how a list works, and that's what a list is. You can have a list of bullets, right? And you can say, what will this list hold? It will hold a bunch of sprites. This list will hold a bunch of sprites. What's the name of this list? It's called bullets. Okay, how do I add things to this bullet list? Well, I can say bullets.add sf sprite, which is my sprite. Okay. How can I access any of these elements? How can I access individual sprites? Well, you say bullets at a specific index dot set position, or whatever it is. As long as you do bullets at index 1, 2, 3, you have access to all the functions of that sprite because you are that sprite. You're communicating with that sprite right now. You're talking to that sprite. So I can access 0, 1, 2, and 3. This is called an index. Indices always start from 0. So the first element is 0. Second element is 1. Third element is 2. If you ever get confused, you always remember the formula n minus 1. If I want the third element, 3 minus 1, I get the index 2. So now I put index 2 over here. Okay? One last thing. This bullets list has a count. Every list has a count, a certain count. This count identifies how many elements in this list. And right now, there are 3 elements. So whenever you visit the count is 3. Okay, because there's 1, 2, 3. There are 3 bullets. How can you access the last element in the bullet? What if I want the last element in my bullet? Is it index 3? No. I have 3 elements, but the indices work differently. Right? Indices start from 0. This is starting counting from number 1. So this is 1, 2, 3. There are 3 elements. But indices start from 0. So this list has 3 elements, and if I want to access the last element, I just say count minus 1. What's the count? It's 3. 3 minus 1 is 2. 2 is the index of the last element. That's something you want to keep in mind also. It's the same concept. It's always the same concept. It's always n minus 1. N stands for the count. How many elements or which element I want. N always stands n minus 1 and always stands to which element you want to communicate with. In my case, I want to communicate to the last element. This bullets list has a variable called count. This count variable will tell you how many elements exist inside this bullet list. So, to figure out the index of the last element, I do count minus 1, which is 3 minus 1, which is 2. The index of the last element is 2. Alright, hope that made sense. This is kind of essential to talk about, and it's kind of important to understand how lists work. Okay, so I've explained the concept of lists. Now I want to dig a lot, deep dive into lists a lot more. I want to tell you internally how it actually works. What happens when you create a list, right? And what happens when you create a variable, and so on and so forth. But I'll keep this for another lecture probably, or maybe later on in this lecture, we'll see. Okay, so this was all theoretical. C++ doesn't have something called a list. It's not called, it has the concept of a list, but it's not called a list. It doesn't have the variable count, it has something else. I've explained only the concept, not the actual not how to do it in C++. Right? C++ has the concept of an add function, but it's not called add. Right? So let's work with this. Let's see how this all works in C++. Well, to substitute a few things, list in C++ is called, and I know it's going to be confusing, it's called a vector. Don't confuse SF vector from std vector. They're completely 2 different things. SF vector, a vector, whenever we're talking about vector in the concept of game development, a vector is a dot and a direction with a specific magnitude. It's an arrow that points in a certain direction with a certain magnitude, how long the vector is, when we talk about vectors. In C++, vectors are lists. So don't confuse those 2 things. I don't know why they called it a vector in C++. No idea. That's what it's called. So, a list in C++ is a vector. Whenever we want to add something to this vector, we use the function, not add, but we use the function called push underscore back. Not push, P-O, this is a U. Push back. So add is pushback. To get the size of my list, how many elements in my list, we don't say count, we say size, and size is a function. So if we do bullets, so here, if I say bullets dot size, I'm now talking, notice I'm talking to the bullet list itself. So I get the size of the how many elements in my bullet. However, when I do bullets at 0, now I'm not talking to the list anymore, or I'm not talking to my vector anymore, I'm talking to the sprite itself. That's it. That's all the differences. A list is called a vector in C++. To add an element to that list, we use the function pushback. To find out how many elements in this list, we use size, not count. Right? So those are kind of the things that I want to cover, and how to use lists and so on and so forth. Now, there's so much I would like to deep dive into vectors and how they work, but we'll talk about that a little bit later. Okay? Now, one thing before we jump into C++ and kind of write all this up, I would like to talk about the concept of a loop. And we already touched on that subject before, right? We said that right now, if I go to my code, we have two loops, right? We have the game loop, which is while window is open, and the event loop, right? There's two loops. A loop is just something that goes over and over and over. It happens over and over and over. And we're always in that loop, right? So those are loops, something that happens over and over and over. Now this loop, we call this the main loop, and this is the event loop. But while this is true, this is actually called the while loop. Generically in C++, this is a while loop. And this is also a while loop because it starts with the word while. So while a condition is true, do something over and over and over. While a condition is true, do something over and over. So it's called the while loop, but this is our game loop. This is a while loop, but it's our event loop, right? So in C++, there's a while loop, and there's also a for loop. Now, for loop is used a lot, or it's most suitably used for vectors, because I can iterate over, I can go through this list of elements in a for loop. Okay? So I just want to I want you to keep that in mind for a second. Okay, before I create a vector of sprites and we add something to sprite and so on and so forth, I would like to make this a little bit easy and kind of practice on vectors a little bit, right? So what I'm going to do at the very start of our program, so this is our program, at the very start, I'm just going to click a bunch of enters, right? Our code's still there at the bottom, but I want to practice a little bit with vectors and talk about vectors and how we use them. Okay, so how do we add a vector? Well, essentially, the first thing you need to do is include a vector. Include the vector header or the vector file. So just do include vector. Next, I need to create a vector. What I'm going to do is I'm going to create a vector of type string, because the program that I want to type is top 10 favorite video games, right? I want to list top 10 favorite video games. Okay, so let's create our vector. Our vector, we start with std vector. And then we create these arrows. Inside these arrows, I need to provide, or I need to tell C++ what kind of vector is this? What data type does this vector hold? And remember, in here, a vector is just a list, and it has elements, element. So what data type is this element that I'm gonna store in here? What is it? Well, in my case, I'm not gonna do a sprite. Okay, I want to list the top 10 favorite games. So this is gonna be text, and text is a string. So I'm gonna do std string. So this vector is gonna hold a string or multiple strings. Each element in this vector is going to be a string. Okay, so now that I've mentioned the data type of my vector, what it's gonna hold, I need to name my vector so I can use it later on. And here I'm gonna say top video games. So now my vector, I created a vector. This vector has the name top 10 video games. This vector is called top 10 video games. This vector holds a bunch of strings. Right now, currently, this vector holds 0 elements. It holds nothing. We want to add things to this vector. How do we do that? Well, pretty easy. You take the name of the vector, right, which is top 10 video games, dot, remember, pushback. Pushback is a function that takes as an input whatever data type you provided here. So if this would have been an integer, then the input here would be 10. If this was an std string, then the data type would be a string. For example, David. If this data type was an SF sprite, then I have to provide an SF sprite over here, right? So whatever data type is in here, I want to add to that list. So in my case, it's a string. I have a list of strings. All right, so let's add our first element. What are my top 10 favorite video games? Well, we'll start with the Final Fantasy series. So Final Fantasy 7. Next, Final Fantasy 8. Next, Final Fantasy. I was confused 8 and 9. I think 8 is the one with Vivi, and 9 is the romantic story. Let me double check. Final Fantasy. I was confused the two all the time. No, yep, I confused them. It's Final Fantasy 9. God damn it. Alright, so Final Fantasy 9, not 8. And then Final Fantasy. I like 13. Actually, I like 14 more than 13. And then I like 13. 13 was good, even though a lot of people hate it. I love 15. 15 was good. Right? Let's add something other than Final Fantasy. Let's say Doom. I like Doom. I like Quake. What else? Need for Speed. I love the Need for Speed series, especially Underground 2. Need for Speed Most Wanted was good. The 2005 one, not 2012 one. 21 is garbage. Need for Speed 2015. Is it 2015? I think, yeah. Such a good game. Such a good game. And then Forza Horizon 5. I've been playing it a lot. It's really good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Damn it. Alright, I need to remove a game from my list. You know what? No, I need to remove a game from my list. A lot of Final Fantasy here. I'm just gonna say Final Fantasy. Let's do Final Fantasy. Alright, Doom, Quake, 190 for Speed. What else? What else do I like? What else? What other video games do I like? Ooh, Battlefield. Battlefield Early Access. It's coming out. Battlefield Bad Company 2 was top-notch game. Battlefield 242, 252, 242. What the hell's which one is coming? Battlefield 242. Yeah, it's coming out tomorrow. Can't wait. I played it. I played the beta. Such a good beta. What else other than Battlefield? What else? What else? What else? What else? What else? Man, I need to check out my Steam library. Good lyric. What else? Final Fantasy. Forza. GTA is good. Half-Life is fantastic. Half-Life. GTA. 3 was good. 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, that's enough. Not 3, is it? Yeah, it's 3. Cool. All right, so this is a list of my top 10 favorite games. All right, now how can I display it on the screen? I've added all of these into this variable, which is top 10 video games, right? So this variable now holds my top 10 favorite video games. How can I display it? Well, I can do std cout top 10 video games. But hold on a second. I can't display the entire list. I can't just do this. Right? If I want to print the entire list, I can't just say top 10 video games. That's not going to work because a vector is not printable. I can't just print the entire vector. So how can I print the entire vector? Well, I have to print element by element. Right? I can't print a vector, but I can print a string. So how can I access a string? Remember these brackets, and I put the index number that I want. I'd like index 0. Then I have to do this 10 times. Index 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this will print Final Fantasy. Right? This will print Doom. This will print Quake. This will print Need for Speed 2. Underground 2. This will print Need for Speed Most Wanted. Need for Speed 2015. Forza 5. Bad Company 2. Half-Life. And GTA 3. Right? And notice, index 0 is the first element. Index 1 is the second element. 2 is the third element. 3, fourth element. 5, fifth element. 4 is the fifth element. 5 is the fifth element. 6 is the... I get confused now. But anyways, 0 is the first and so on and so forth. The 9th element is the 10th element. Okay, so number 9 is the 10th element. 0 is the first element, and so on and so forth. So now if I press play, you'll see that are printed in this order. Forget about their game for a second. You can see Final Fantasy is first. So index 0, Final Fantasy. Doom, Quake, Underground 2. Right? Spread it side by side like that. Right? Doom, Quake, Underground 2, Most Wanted. This, Forza, Battlefield Bad Company 2, Half-Life 3, then Skeleton Loaded, whatever, in order with that, right? There you go, which is super cool. So I can print every single element by tapping its index. What if I only want the first element? So I can just delete all of this, and this should print only the first element, which is Final Fantasy. Right? What if I want the fifth element? I would like the fifth element. So the fifth element is 5 minus 1, which is 4. So the fifth element is 4. So this is 1, 2, 3, 4, 5. This is the fifth element. 1, 2, 3, 4, 5. The fifth element is index 4 because we count with indices, we count from 0. 0, 1, 2, 3, 4, which is this one. Need for Speed Most Wanted, right? I was gonna print Need for Speed Most Wanted. Most Wanted is 1, 2, 3, 4, 5. But index 4 is 0, 1, 2, 3, 4. Right? Just always keep that in mind. Alright, cool. What if I want to print the last element? Well, it's index 9. Right? Because the last element is index 9. I have 10 of them, but the last one is index 9. There you go. GTA 3. What if I print number 10? I don't have 10 in my list. What if I print it? Well, the application should in theory crash, which it did. Right? So it crashed and gave me an error, and it jumped to the vector class with like a weird thing and said, an invalid parameter was passed to a function that considered invalid parameter fatal. So it went to this very scary, very, very scary source file, which has code that doesn't make any sense. All right, now here's a problem, right? This is a perfect time to kind of teach you how to debug this. Because if you didn't know, so let me close this class. If you typed 10 by mistake and then you press play and you got an error, and if you press ignore, it took you to this class. Now you don't know what the hell happened. You're just in this weird class, you know, and you're in the vector class and you don't know what's going on and you're kind of worried, right? Well, the cool thing about a debugger, right, which we have a debugger, and we said that debugger is a software that helps you debug your program, figure out what's going on in the program. Well, our debugger right now, there's something called a call stack. Pick a different color. And you can see here there's a window, right? And this, you can see here, called call stack. This is my call stack. A call stack is literally a list that keeps track where we were before, where we came from, where we are in the program. So to give you an example, a call stack would say we started at line 5. Well, this is not completely true, but for now, let's assume it's true, okay? So a call stack keeps track where we are in the program. So we say we're at line 5, then we move to 6, then we move to 9, then we move to 11, 12, and so on and so forth, and then we jump into 22, right? And so on and so forth. So a call stack just keeps a history of where we were in the program. It doesn't work exactly like that, like I mentioned here. It works with functions. So it jumps from one function to the other. Right? And I'll cover call stacks later on in a lot more in depth. But all I want you to know and remember for now is that call stacks allow you to figure out where you were in the program and kind of jump back to a previous state in the program. So here's the thing. Right now I'm in this scary file. If you look at the call stack, it says we're on this line. And how do I know? It's because there's a yellow arrow on this line. So if I look at this, this is grayed out. This text is grayed out, which means I cannot go there. This is grayed out, I cannot go there. This is grayed out, I cannot go there. This is white. This text is white, which means I can jump in here. So if I double click on this, it takes me to line 22. So now I know that in the call stack, what happened is that I went here, I jumped into, I created this list, I added all these elements to the list, and when I tried to print the 11th element, not the 10th, this is not the 10th element, this is the 11th element, because number 11, we didn't add number 11. So when we try to print the 11th element at index 10, it crashed and it failed because there is no element 11. And so now I'm looking at this, I jumped here, right? And I know at line 22, I look at line 22 and I look at it, it's like, okay, why did you crash? Oh, okay, so this is 10. Oops, I'm supposed to type 9, not supposed to type 10. So I stop my program. I change that to 9, and I press play, and my application should run just fine. Right? So the call stack is very important. It's very, very helpful. It allows you, if your application crashes, it allows you to figure out where were you before it crashed. Right? We can jump back. We jumped into this file. We can jump back by just clicking on the white line, the first white line we see. In this case, it says RPG game line 22, which we're here, and we see what's wrong. Cool? So that's kind of like a brief introduction to call stacks. I'll deep dive into call stacks a lot more later on. Right? But anyways, so now we have a vector or list with a data type of a string, a variable with my top 10 favorite video games. I'm adding my top 10 favorite games and printing the 9th element. Okay, so that's all cool and well. And before that, what we had to do is we had to print, if I wanted to print the entire list, I would print every single element individually, which is not great. Is there any way to print this faster? What if I have 100 elements? Do I really have to type all the numbers 0, 1, 2, 3, 4, 5, and so on and so forth? Well, no. We have a loop, remember? You can either use the for loop or the while loop. Both of them work just fine. But the for loop is more targeted to kind of vectors and things like that. It's It's a little bit easier to work with. I'll show you how to use both, but we're going to start with the for loop. So how can I loop? So my objective right now is to loop through this entire list. I'd like to loop through this entire list and print every single element in my loop. Without the loop, we have to do this. Okay, so let's see how we do it with the loop. So under this code, I'm just going to comment out all of this code for now, because I would like to use it later on. I'll show you the differences. So I comment all this code. And let's start with a loop. How do we write a loop? Well, it's called a for loop. So a for loop starts with the word for. So if I type for, like that, okay? Now, from here, I can either type the loop manually, or I could let Visual Studio type it up for me. Okay, so let me start by typing it manually. So do this, brackets, int I equals 0. I create a variable called I, make it equal to 0. Then I say I is less than 10. Okay, and then I say I plus plus, and this is my for loop. This doesn't make any sense, or not quite much sense to you right now, but this is a for loop. So I typed it manually. How do I let C++ do it for me? Not C++, Visual Studio do it for me. Well, the cool part is I can type for, all right? You can see IntelliSense is going to open a window for me, and you can see the first option is for. So if I double click on this, it creates the entire loop for me, which is cool. Okay, how do I do it without using my mouse? Well, again, if I type for, I'm going to double click the tab key. So on my keyboard, there's a key called tab. If I double click it, or actually I click it once. Well, once or twice, doesn't matter. It auto-completes it for me, which is cool. All right, let me explain now what a for loop is. Well, a for loop is a loop that does something over and over and over until a certain condition is met to exit the loop. So in my case, a for loop has two brackets, right? An opening and close bracket. This loop has 3 sections. So I'm just going to type 10 here, so this error just goes away. Okay. This loop has 10 sections. This is the first section of my loop. This is the second section in my loop. Section. This is the second section. And this is the third section of my loop. All right. So let's start with the first one. The first one, the first section, is where you initialize or create your variable. So what I've done here is I've created a variable called I. This variable has a data type of size underscore t. And we covered size underscore t very briefly last time. We said that size underscore t is the largest data type that C++ can have on your current machine. So that means if your machine is running a 32-bit operating system, or you're running a 32-bit program, then size underscore t will be 32-bit, which means it will have a maximum value of 4 billion numbers. Okay? However, if you're running on a 64-bit machine, that means size underscore t is going to be 64-bit, which means this value is going to be, I don't know, 18 something. It's a really, really large number. Just do 2 to the power of 64, essentially, right? So underscore t, the value, or sorry, the size of underscore t, how much data it holds, is dependent on the software, the operating system, and the processor. So this is the largest. But it will always be the largest possible value, or the largest variable that your program can hold. In which case, we have 64-bit, which means that this is a 64-bit value, or variable. Well, 64-bit data type, not either of these. This is a 64-bit data type, right? Cool. So what I've done here is I've created a variable called I. This data type is size underscore t, and a size underscore t is just a number. So minus 10, full numbers, minus 10, minus 13, 66, minus 100, 199, 0, right? All these are whole numbers. It won't have decimal points, so not 5.3, 3.3f, for example, right? This is an integer, just the biggest integer your system can hold, right? So I'm creating a variable called I. I'm setting the variable I to 0, and the data type is size underscore t. If you don't want size underscore t, you can make it an int if you really want to. In fact, you can make this any data type you want. You can make this an std string if you really want to, right? But this won't make a lot of sense right now. So we'll just we'll keep it as either an int or size underscore t. The point is, the first part of our for loop is creating the variable. I know, right? Who runs 32-bit? Surprisingly, there are a lot of people who run 32-bit. But, so this is the variable creation part of my for loop. All right, the next part is my condition. The condition part is, well, it says this. As long as this condition is true, I'm going to keep executing my loop. So, while this is true, I'm going to do the code inside these curly braces over and 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 over. All right? So that's the condition. Once this condition becomes false, we exit the loop and we go to the next line. So while this is true, I keep going, I keep executing stuff inside. When it's false, I exit. All right, cool. Next. Well, the next part is what happens anytime I finish a single iteration of my for loop. What does that mean? So let's say, for example, in my loop, I said std cout hello, std and l. So in here, in my loop, I basically said I would like to print hello. So I went inside the loop, I printed hello, and I finished the first part of my loop, the first iteration. Now I need to do whatever I said I need to do here. In my case, I said I plus plus. Okay, the question is, what's I plus plus? Well, I plus plus essentially means take the variable I and add 1 to it. I always notice UTK. But yes, so basically take I, the variable I, and add 1 to it. That's what plus plus means. If you do I minus minus, it basically means take I, subtract 1 from it. So let's assume I is currently 0, and I say I plus plus. What does that mean? Well, it means that I've added 1 to I, which is 0 plus 1 is 1, which means I currently is 1. What if I do I plus plus again? Well, I is 1, 1 plus 1 is 2, so I is now 2. So every time I do I plus plus, I increment by 1. Anytime I do I minus minus, I decrement by 1, which means if I is, for example, is 3, and I say I minus minus, I becomes 2, because 3 minus 1 is 2. So what I'm saying here, that every loop iteration, every time I go here, print hello, and when I'm done printing hello, I should increment I by 1. So I increase I by 1. Right? Okay. So this makes sense now, hopefully. This part is creating the variable. This is the condition, and this is what I do every time I finish the iteration of my loop. All right, so let's go through this. Let's actually go through this loop manually. Instead of 10, I'm gonna do 5, because 10 is a lot. So let's see what the compiler is doing. Let's see what the program is doing. Well, the first thing, it's gonna go to line 35. Line 35, it's gonna create a variable called I of data type size underscore t, and it's gonna assign the value 0 to it. Next, it's going to check if this condition is true. I is currently 0 because we assigned it to 0. So now we ask ourselves, is 0 less than 5? Is this a true statement or not? Well, mathematically, 0 is less than 5. Okay, fantastic. So now we execute what's inside this loop. So now I print hello on the screen for the first time. I finish what I execute all the code between the curly braces, or in this loop. Now I need to execute. I go over here and I execute this part of the loop. So now I plus plus. So now so I was 0. Now I is 1. Now that I finished executing this, I go back to this condition and I check. Right? Now, I became 1. So now I check. Is I less than 5? I is 1. Is 1 less than 5? Yes, 1 is less than 5. I execute another hello. And then I go back and I increment I by 1. So now I is 2. Cool. Now that I'm done incrementing I, or now that I executed this part of the loop, I now go to the condition again. What is I? Well, I is 2. Is 2 less than 5? Yes, 2 is less than 5. I print hello again. Right? And then I increment I by 1. I now becomes 3. When I'm done with this part of the loop, I check my condition again. What is my condition? Well, my condition is I is less than 5. What's I? I is 3. Is 3 less than 5? Yes, I print hello. Okay. And then I increment I by 1. So now I is 4. I check my condition again. Is 4 less than 5? Yes, 4 is less than 5. I is less than 5, 4 less than 5. I print hello. I increment I by 1. I becomes 5. Okay, so now the question is I less than 5? What's I? I is 5. Is 5 less than 5? No, 5 is not less than 5. So we exit the loop immediately. That's it. That's how for loops work. So let's see how many times we printed hello. We printed hello 1, 2, 3, 4, 5. We printed hello 5 times because in here in the condition we said do this loop until I is less than 5, which means, and I started at 0, which means we did this 5 times. That's how a for loop works, essentially. Right? And that's really, really cool. And we can test this. If I press play, you'll see that this is the case. So it's going to print hello 5 times. You can see 1, 2, 3, 4, 5. So when we create the loop, we create the first part is creating the variable. Second part is the condition. The third part is what we do after we finish every iteration of our loop. Once we finish the first, so this essentially, the first part only happens once and only once. This happens, we check this condition every single time, every loop iteration, and every loop iteration, we execute also this part. So we create the variable, we check, is I less than 5? If it's true, I execute this line. When I execute it, I increment I by 1. When I'm done, I check, is I less than 5? Yes, I execute. I go I++. Is I less than 5? Yes, I execute. Increment, check, is I less than 5? Execute, increment, and so on and so forth, and so on and so forth. That's how for loops work. All right, so this is great, right? This is nice. We made a loop that prints hello 5 times. Great, whoopee. How is that going to help us at all in our code for the std vector? Well, ladies and gentlemen, if you'll notice here that every time I would like to print an element, I take my list, the name of my list, and I mention which element I want to print. And specifically the number of the element that I want to print, or the index. So this index 0, index 1, index 2, 3, 4, 5. So rather than actually writing the code 10 times to print this 10 times, what I can do is copy this and paste it here. Okay. So what is this going to do? Well, this is going to print the first element 5 times, because I'm saying stdc out, print element 0, which is Final Fantasy, and I'm doing it 5 times. Right? So if I press play, it's going to print Final Fantasy 5 times. Right? That's not helpful. I want to print all of the element, not something 5 times. Well, notice what happens here. If I replace this 0 with the variable I, what happens now? Well, I starts at 0. I print top video games at index 0. I increment by 1. Is 1 less than 5? Yes, 1 is less than 5. I go and print top 10 video games at index 1. So now I printed the second element. I increment I check the condition. Is 2 less than 5? Yes, 2 is less than 5. So now I print at index I, which is now 2. So I print the third element. And then I increment. And then this is 3 and 4 and 5. So now I printed the first 5 elements because I is always changing. The variable I is incrementing every single time, which is super, super cool. So now with this code, I am printing the first 5 elements. So 0, 1, 2, 3, 4. The first 5 elements. So if I press play, I should print until Need for Speed Most Wanted, which I do. So I printed all 5 elements, or all 5 elements in my list. Okay, what if I want to print all 10 elements? Well, I do 10. I is less than 10. As long as I is less than 10, then it should print everything. So now I printed Final Fantasy, Doom, Quake, Need for Speed Underground 2, Need for Speed Most Wanted, Need for Speed 2015, Forza Horizon 5, Forza Horizon 5, Battlefield Bad Company 2, Half-Life, and GTA 3. Cool? Now what if I make this 11? Well, again, it's going to crash because there is no 11th element. So we're going to have the same error we had before when we said print top 10 video games at element 10. At index 10, sorry. So now we go here, we double click on our call stack, and we go back to this line. Right? So make sure this is an accurate number. Okay. Well, here's a problem. If I make this 10, okay? Let's say I make it 10. And then later on, I've decided to add one more element in my list. Let's say my next favorite video game is, what's a cool indie game? Diablo. I love Diablo. In fact, Diablo should be at the very top. But we'll just put it at the very bottom, right? I added Diablo. Well, currently with my for loop, I say I want to print the first 10 elements. But right now, I don't have 10 elements. I have 11 elements. You can see 1, 2, 3, 4, 5, 6, 7, 8. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 elements. And my loop is only to 10. So now, let's say I added one more element and I forgot to update this code. Now I have a bug in my code. I have an issue. But I'm only printing the first 10. I should be printing all 11 of them. Right? You can see Diablo is not being printed. Last one is being printed, GTA 3. So how can we fix that? Well, we can look at the error, look at the bug, and I'm like, oh, okay, cool, I forgot to do that, so let's fix it manually, and now do it 11. Now if I press play, I'll have Diablo printed here, right? But this bug can occur over and over and over again. How can we just prevent it altogether? Well, like I mentioned here in the slide, I said that you can get how many elements a list has. So my bullets has 3 elements, and I can get the size of this list, how many elements in that list, by using size. So instead of 11 here, what I can do is say, what's this called? Top 10 video games. I can say top 10 video games dot size. And size is a function. This size function is going to return a size underscore t. So in here, I am setting I to 0. I'm checking if I is less than the size of my list, which in my case is going to be 11. So if I press play, I should print all of them until Diablo, right? You can see until Diablo. Let's say I want to delete all of them and I only want to keep the first 3. So now it should only print the first 3 because size now became 3, right? It automatically detects how many elements you've pushed or you added to this list. So now we prevented this bug, which is great. All right, so we talked about lists. We know how to use lists. Lists are fantastic, right? We know how to use loops. Loops are great. how can we actually use loops in our game, or list and loops in our games? How do we do the whole bullet thing? Well, before I jump into this, before I do bullets, let me talk about how lists work from underneath, because it's really important to understand how lists work from underneath. Okay, so I have my list and I add things to my list. That's great. That's fantastic. If I move to the side here for a little bit, let's talk about memory. Because as a programmer, your number one job, not only to write logic and write code, but also to manage data and move stuff from memory and be able to use memory effectively. So, let's say you have 16 GB of memory. All right. So this is kind of going to be hardware architecture part 2, I suppose. Let's say you have 16 GB of memory. Now, in the old days, right, way back when MS-DOS was a thing, and just in case you don't know what MS-DOS is, MS-DOS was the first operating system that Microsoft created before Windows ever existed. And it looked like this. When you turned on your computer, you just get a black screen with white text, and you would type in that screen to open whatever program you wanted. And you didn't have multitasking, you couldn't have more than one application open at the same time. It was just a single operating system that runs a single application. And it was called MS-DOS. And Microsoft, by the way, kind of stole this, right? But I digress. There's a whole history behind this. I won't get into it too much. Back in the old days, what did you have? Like 256 KB, right, of RAM? Or that was really fancy. You had like 32 KB, kilobytes of RAM on MS-DOS. Now, whenever you wanted to communicate with RAM, so this is your CPU, right? So this is your CPU. Whenever you want to communicate with RAM, your CPU can communicate with RAM directly. As a programmer, you can add variables, and you would program in BASIC or assembly. And as a programmer, you would add variables into RAM. Like you would create an integer called health, right, equal to 5, and then the operating system will just kind of add that variable somewhere in memory, and it'll create a box and it'll have the value 5 inside it, and that's your health. And I'll just make a reference to it, be like, hey, health is this box. If the programmer asks for health, go here, retrieve the value 5, right? So back in the day, programmers had direct access to memory or to RAM, like immediate direct access. Okay. However, in the 21st century, or when Windows came out, I'm not sure when that happened, maybe Windows 3.1. And again, as a history lesson, if you don't know what Windows 3.1 looked like, you should really go check out the history of Windows. It's really fascinating. Windows 3.1 looked like this, which was pretty cool, right? I remember this so vividly, like it was yesterday, right? You had multitasking, you had that concept of Windows, like an actual window, which was pretty cool, right? 3.1 was the third version. 1.0 was the first one. So you had Windows 1.0. I don't remember 1.0. I remember 3.1. I was too young for Windows 1.0. I remember 3.1. Anyways, so when Windows came out, I don't know which version of Windows, but so it could be Windows 3.1, could be Windows 1, could be Windows 95. I don't quite remember. But let's say it was Windows 95, for example. Windows 95, normally back then, you would have had, what, 16 MB of RAM? That was huge. You had 16 MB of memory, right? So here's the problem though. Now as a programmer, this is the CPU. Now as a programmer, this is RAM. You don't have direct access to memory, right? The operating system is not gonna let you access memory directly for many reasons, of which I'll go through right now in a bit. But instead of the operating system, or instead of the operating system allowing you to access memory directly or RAM directly, what it does is when you have an application, or when you open an application and program an application, you actually, the operating system will create virtual RAM for you, or virtual memory. That means your application doesn't interact with RAM directly, it interacts with virtual RAM, a concept that the operating system creates for you. And when you create a variable in virtual RAM, the operating system will map this into actual memory and post it in memory in the actual location. So let's say in virtual RAM, you manage to say, I would like to have a variable over here. Actually, in RAM, it might not be at the top, right? It might not be at the top because you're not talking to RAM directly, you're talking to virtual RAM. So if you create it at the top, it might be here at the bottom, for example. So each single instance of an application, every single application had access to virtual RAM, and whenever you created a variable, the operating system would put that variable in RAM. It will map it into RAM itself. Okay, so the question now, why the hell are we doing that? Why can't we just access RAM immediately? Well, one of the things is security. Imagine if you written a piece of software that would write into a location in memory where other applications live. So for example, let's say this is your software. So this is my cool software, SF for software, right? Let's say you're playing a game at the same time. What's a popular game back then? Let's say an MMO or Halo. Let's say Halo. You're playing Halo. Halo is on Mac. Say you're playing Neverwinter. Neverwinter. Okay? Playing an MMO called Neverwinter. I think that's what it's called. And you have an amount of gold. Let's say your gold is 500. You have 500 gold. Okay? If the operating system allowed you to access memory directly, what you could do is figure out where this variable is in RAM. All right? And with this application, you would go and change this value yourself, because you don't have the concept of virtual RAM anymore. All of the applications are using the same memory. So now I can figure out where this application is storing this gold, and I can go change it. So instead of 500, here 500, instead of 500, I can make it 1000 and increase it by another 500, right? If everything shared the same memory pool, right? And so that's why the operating system gives each single application its own virtual memory. So this has its own virtual memory, which if it fucked up, if it did something to it, it cannot interact with our other application. It cannot mess with other application. It will not be able to crash another application. So imagine if I'm a programmer, I'm writing a piece of software, and I fuck up somewhere, and the same thing I did here. I try to access an element that I can't access, and I write something to it. And when I write it, I basically am changing the state of another application, and so I crash another application by me programming something here, or crashing Windows altogether. That'd be really bad. So what the operating system did is created virtual RAM. Any software, it works in this virtual RAM, not directly, so the application doesn't affect RAM directly and fuck up something directly. Now, let's be 100% clear. You still can create a software that goes and change the state of different software. And that's how cheating tools work. That's how, if you have a cheat on your game, like Call of Duty, Battlefield, whatever game you're making, or whatever game you're playing, if you have a cheat software or a hacking software, well, cheating software, that's what the application does. It actually finds out where a specific variable is in memory and it modifies it. Right? Even though virtual RAM exists and virtual RAM exists right now and we use it, right? It does that. I don't know how it does that exactly. I'm not too familiar with cheating tools, but that's literally what it does. The cheating tool will go find where this variable is in memory and it changes its values. That's kind of the overall concept of virtual memory and how it is right now. All right, so that's kind of memory and RAM. So RAM is just a big RAM is just a bunch of RAM is just a big table, right? Lovely table, which a piece of software uses, right? So let's say a piece of software is using this part of RAM, another piece of software is using this part of RAM, right? And your variables exist in this location over here, and variables exist in this location for this software, right? Different locations, and you're just doing and stuff. When you create a variable called health, it will go and find the location in RAM. Let's say this memory address here, it finds the location and puts 5 here. Health, my health is 5, right? And it just names this part health. So now if you want to read health or if you want to write to health, it'll go to this location in memory and change it, right? So that's kind of how RAM works, right? Now it's very important to also understand that every one of these cells, every single one of these cells has something called a memory address. And the memory address is just an address for this specific cell. It's like you have a house, and if you want to tell your friend, hey, dude, can you please come to my house? Oh, I want to play, I don't know, I want to watch Game of Thrones, or I want to play a game. So he asks, okay, where's your house? And you give him the address of your house, right? Where it exactly is in the country. So that's what a memory address is. A memory address is a location in memory. And memory addresses usually, or not usually, memory addresses are hexadecimal values. Hexadecimal values, so you have decimal, right? Decimal numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. No, sorry, 0 to 9. These are decimal values, right? Our decimal system is 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 digits. It starts from 0 to 9. That's our decimal system. Binary is only two digits. Binary is just 0 and 1. That's the binary system. Hexadecimal is 16 digits. And it goes something like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, A, B, C, D, E, and F. 16 numbers. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Whoops. Well, that was a nice 16. 16, right? So hexadecimal, or hex, called hexadecimal, hex, is 16 digits. Decimal, DEC, is 10 digits. Binary is 2 digits, right? So a single memory address is a memory address that is hexadecimal. So for example, the first cell in our memory is set to 0, x, 0, 0, 0. or x00. This part, this 0x, indicates that this is a hexadecimal number, right? So that's the first cell. What about the second cell? Second cell would be 01. Third cell, 02. Fourth cell, 03, and so on and so forth. Okay? What about the 10th cell? Well, let's do this. Let's go through all of them. I need more space though. Let's go here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What comes as 12? 13, 14, 15, 16, right? So the 16th cell, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The 16th cell is 0x, 0f. And then we do 17. How do we do 17? Well, 17 is 10. 18 is 11. 19 is 12. 20 is 13. Right? And so on and so forth. How did I come to this conclusion? How did we do this? Right? So now we're kind of talking about decimal binary. Well, think about it. Once we reach the last digits in our decimal system, we reset this to 0, this resets to 0, and the next digit increments. Right? So look at this. We have 0, 1, 2, 3, 4. Okay, let's do two digits. This is normal decimal system. This is our normal number, everyday number. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9. We reached 9. What the hell are we gonna do? We finished all 10 digits. We reached our limit. 9 is the last digit. What do we do? How do we keep counting? Well, we reset this to 0, and then we increment this by 1. So what comes after 9? Reset this to 0, 0, increment this by 1. 10. What do we do after 10? Well, keep incrementing this part. 11, 12, 13, 14, 15, 16, 17, 18, 19. We reached the limit again. The hell are we going to do? 9 is the last digit. Well, reset this, 0, and increment this by 1. 20. Reset to 0, and increment by 1. And so on and so forth. And that's how numbering systems work. And the same thing applies to hexadecimal. Hexadecimals, they go 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9. What comes as 0, 9? 0A, 0B, 0C, 0D, 0E, 0F. We reached the limit. We got to, right? We reached the limit. We got to the last digit. It's F is the last digit. What do we do? Reset this and increment this by 1. So 16 would be 1, 0. And then 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 17, 18, 19, 1A, 1B, 1C, 1D, 1E, 1F. We reach the last digit. What the hell are we going to do? Reset to 0, increment by 1. Reset to 0, increment by 1. 20, 21, 22, 23, and so on and so forth. And you keep counting. That's how all numbering system works. Every single numbering system. That's hexadecimal, that's decimal, that's different numbering system. Why do we use hexadecimal? Because it's more compact. I can have a lot more digits in this numbering system, which is kind of cool, right? That's why I use hexadecimal. So every cell, I hope this made sense, every single cell in memory has a hexadecimal value, not the value, hexadecimal address. So if I want to talk to this cell, this has an address. What's the address of this cell? Well, let's count. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D. This has a hexadecimal address of 0x0D. Why do we do 0x? Because hexadecimal, we say if we want to mention that this is a hexadecimal number, we do 0x. So 0x0D. So this is D, right? So the address of this cell is D. The value inside it would be, for example, 5. So again, 0, 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, A, B, C. D was over here. I messed up. 5. 0D is over here, right? So 0D, the address 0D has the value 5. Now when we're programming, we don't refer to a cell in memory by its address because we don't know its address. Well, that's a lie. We do know its address. We're going to find out its address later on, but we refer to it with the variable name. So 0D, otherwise known to us as health. So the variable name, whenever we say int health, this variable, and we say equal to 5, health is a nickname for a memory cell in memory. So the nickname of this cell is health. Its actual address is 0x0D. Now, whenever we run our program, we always store in different cells. We're never going to store, our application is never going to use the same cell address. The operating system randomizes the addresses every single time for security reasons. Because imagine if you have the same program running all the time and it's accessing the same memory address every single time, you can have some serious security issues, right? So every single cell, every single memory cell has a memory address, which is a hexadecimal value, right? And whenever we create a variable, when we say int health, health is just a nickname for a memory cell, which has an actual address. In our case, the address here is 0x0D, right? So that's just something to keep in mind. Every cell has a memory address. Cool. All right. Now that's your introduction to kind of RAM and how RAM works. Well, not how RAM works, how we deal with RAM and how that every memory cell has its own memory address, and whenever we create a variable. So whenever we create a variable, the operating system will be like, okay, there's a location that's free over here. This is a free location. Well, I'm going to add the health variable over here. Well, that's not really how it works. Not technically, not completely. Because whenever you create a variable like this, it gets pushed to something called the stack. Okay, this happens when you're using the heap. We haven't talked about the stack and the heap yet. So for now, all I want you to know, for now, that whenever you create a variable, the operating system will be, okay, cool. There's an empty space over here. This cell is empty. What's the address of this cell? Let's say 0x15. This is the memory address of this cell, for example. I'm going to put a value of 5 in there. So or 10. I'm going to put the value 10 in here. All right, and okay, he wants me to refer to this as damage. Okay, cool. So 0x15 now is also referred to as damage. So whenever I say damage equal to 2, or whenever I say stdcout damage, I go to this memory cell, I grab with this specific address, I grab the value and I print it or write to it or do whatever I want to it. Right? So that's how kind of memory works and how every single cell in memory has a certain location, which is cool. All right? Okay, so now that we know how memory works, what the fuck does this work? Why are we talking about memory for this? We're supposed to be doing bullets. Why are we talking about this? Alright, so I'm gonna cover this last thing and I'm gonna end the lecture here. We're an hour and 40 minutes in. I don't want to stay here for too long, right? But how does this work in terms of list or in terms of vector? Well, we know that whenever we create a variable, whether it's an integer, a float, a string, whatever, the operating system will go find an empty location. It's gonna put the value here. So let's say this is a string and I put David here, right? This memory cell has an address of 0x FA, for example. This is the memory address of my cell. Okay, and it has an alias. Sorry, I hit the mic. It has an alias of, I don't know, name. So this is my variable. So whenever I did std string name equal David, when I did that, right? So when I created the variable called name with the data type string with the value David, the operating system will go, okay, cool. This is an empty location. Okay, this memory address is called 0FA. This over here is the memory address, the actual memory address of it. Okay, that's cool. I'm gonna nickname it to name. So now whenever I say name, I should know that I should go to this memory address. Cool. He wants me to put this value over here. All right, I'm gonna save David in this cell, which is 0xFA, but it's actually called, he nicknamed it as name. All right, so when I do std cout name, std endl, right? Whenever I do this, what does it do? Well, it says, okay, I'm gonna print something on the screen. Oh, he wants me to go to this variable called name. Ooh, I've seen this before. Name has a memory address of 0xFA. Okay, let me go there. Go to memory. Oh, it's over here. Okay, cool. What's the value here? Oh, it's David. Okay, cool. I'm gonna take David, print it on the screen, and put a new line. That's kind of how that works, right? That's how memory works. That's how you write to memory and how you read from memory. Okay, cool. How does this work for lists? Because a single variable, right, is just a single cell. But a list is not a single variable. A list has multiple variables or multiple elements, right? We need to store multiple things in here. How do we do that? Well, how a vector works essentially works something along these lines. Whenever I create a vector, so std vector, we're just gonna make it a vector of integers for now and call it phone numbers or ages. Ages. Whenever I do this, I basically say, okay, you know what? You know what I'm gonna do? This guy, okay, wants a variable which has a location in memory. So what I'm gonna do, okay, so this is one location over here. So let's say this is, whenever you see X, that's busy, right? It's not empty. It's not an empty location. Okay, so let me delete this part over here. We'll just fix up this table real quick. Oops, wrong color. Okay, so this is an X, and the X over here, and the X over here. Okay, so every X you see is busy, right? I cannot, there's already data in here, cannot be used. So whenever I do this, and I add an element to it, so I say age dot pushback the value 10, right? Whenever I do this, how this works, it's going to be like, okay, he wants me to add the value 10. Okay, so here's the thing. He wants me to add the value 10. It's a single element. But I think, just to be safe, what I'm going to do, I'm going to reserve 4 elements in memory for him. Okay? So 4 elements in memory. And so if he adds an element next time, I already have that location reserved, which is kind of cool. Right? So it goes and checks and goes like this. Does this fit 4 spaces? No, this cannot fit 4 spaces. This fits 1 space, 2 spaces, but there's something in here. So this will not work. Okay? And then it goes like, okay, can I fit 4 spaces here? No, there's only 3 spaces, so this will not work. Can I fit 4 spaces here? No, doesn't work. This doesn't work. There's a location here. Can I fit 4 spaces here? Well, I can fit 1, 2, but this is used. And this is only 2. It's not gonna work. It's not gonna work. None of that worked. None of this worked. None of this works. Oh, cool! Look, there's 1 location over here, 2 locations, 3 locations. Oh, cool! 4 locations. So I have 4 locations. Okay, cool. I'm gonna add 10 over here. That's nice. It's really nice that I found 4 locations. Cool. Nice. Very, very nice. Very, very nice. And then I do age dot pushback, say the value 11. Oh, he wants to add 11. Oh, thank God. I already reserved 4 locations. So you know what? I'm going to add 11 right next to it. Okay. And then I do another pushback for 12. Like, oh, cool. I still have space. So 12 over here. And they do another pushback. Let's say 13. Like, okay, cool. There's still space. 13. That's nice. And then I add another element, 14. And I go here and look. Well, I only reserved a space for 4 elements. And I ran out of space. There isn't enough space anymore. What am I going to do? Well, this is what it does. It's now going to look for a new location in memory to find a location that fits not 5 elements, because there's 1, 2, 3, 4, and this is the 5th element we're adding. Not 5 elements. It's going to look for 8 elements. So let's assume, for argument's sake, we freed some memory, right? And this now became empty. This now become available. And so we now check, are you empty? Yes. Are you empty? Yes. Are you empty? Yes. Are you empty? Yes. So we have 4 empty. That's good. Are you empty? Yes. Are you empty? Yes. Are you empty? Yes. Are you empty? Yes. Okay, cool. We have all of 8 elements. Okay, so here's what I'm going to do. I'm going to take this data, copy it, and paste it over here. So let me reserve 10 elements. So this is 1, 2, 3, 4, 5, 6, 7, 8. I have now reserved 8 elements. I'm going to copy this data, paste it here. So 10. 11 goes here, 12 goes here, 13 goes here, and he wanted to add 14. I'm gonna add 14. Cool. So, and then I'm gonna empty this location. I'm gonna free this space. So now this space is freed. If I go like this, this is now free memory. Okay, so now let's say I do another pushback. So now I want to add 15. I check, oh, I still have space for 15. I can add 15. I do 16. Oh, I have still space, 16. I add 17. Oh, cool. I still have space, so I do 17. I add 18. I ran out of space. There's no more space. I only reserved 8 location and he filled it up. What am I gonna do? Well, now I have to find a new location in memory that has not only 4 spaces, not only 8 spaces, but 12 spaces, because 4 plus 4 plus 4 is 12. Whenever I add a new element, I don't just add a new element, the vector will also reserve 3 more locations for me. So I need to find 12 locations, and so on and so forth, and this keeps going. So now I copy this data to a new location. So here, let's say 11, 12, 13, 14, 15, 16, 17, right? And I reserve more. So this is 18, and I have 3 more locations. And if this gets filled up, I need to copy now all of this data, find a new location in memory where it's empty, and I can have reserve more data. Now, this is bad. This is very expensive. Copying data from one location to the other is pretty expensive, and it will reduce your performance, your application performance substantially, which is not good. So anytime, and so the vector knows this, right? So anytime you add an element, not only do you add that element, but you reserve 3 more spaces for future elements that you want to add. If you fill those 3 spaces, you have to copy this data into a new location in memory and fill that up. And that happens every single time, which is a problem, right? And you might wonder, why not just put something over here, and something like there are empty spaces. Why not just put the first 4 elements here, and then the next 4 elements over here, and the next 4 elements over here? Why do they have to be next to each other? Well, specifically because the number one reason is things that are next to each other in memory are a shit ton faster to grab and use than things that are further away. Would it be better for you to go to the store, buy milk, coffee, and bread all in one location, or go to 3 different stores, each one is 5 kilometers apart or 5 miles apart? Which would be better? Going to one location, buying everything, or going to 3 different locations that are all over town? Well, going to one location is better. That's why it's much better if shit was next to each other in memory. It'd be a lot more efficient if they were next to each other than they're all over the place. And so the vector was designed so all of the elements are next to each other. That's the first part. The second part, notice that all of these elements have sequential numbers. The 0, 1, 2, 3, 4, they're all next to each other. How's the list is gonna find index 2 if index 2 is actually somewhere else in memory? It's like over here. Like this is 0, 1, and 2 is over here. This is not gonna work as 2. 2 is supposed to be here, supposed to be next to each other. This is like 11 or whatever, right? So because these are indices and numbers are sequentials, things should be next to each other. And because also things that are next to each other are much faster to grab and use than things that are further away, right? CPUs love things that are next to each other. Your program will perform so much faster if your data is all in one look or next to each other, right? Your CPU loves when your data are next to each other. And so that's essentially how lists work. When you push something to a list, you allocate extra storage so you can use them in the future. And if you run out, you have to copy that data to a new location, which has your current data plus more future allocations, so you can allocate or you can push more things in here, right? So this whole copy paste part and finding a new location in memory where it fits all the things, this whole copy paste is really, really slow, really, really bad. We shouldn't do that much. Okay, so how can we make this a lot more efficient? Well, luckily, whenever we create a vector or a list, we can tell the list or the vector to pre-allocate data. And this allocating data, when we say allocation, that means we reserve allocation in memory. So we can reserve these bunch of blocks in memory. And we say, all of this in memory is reserved for me. Don't touch it. So what I can do is if I know how much data I want in my vector to be added, so let's say I already know that I want top 10 list. A top 10 list means there are 10 elements. So I already know that this list will have 10 elements. So when I create it, I can tell the vector, right? When I create it over here, right? When I create my vector here over here, I can open a bracket here and tell it, I would like you to reserve 10 elements for me. Or I would like you to reserve 100 elements for me. Or I would like you to reserve 1,000 elements for me. So now it's going to reserve 1,000 places in memory next to each other of a data type called SF sprite. And this is super, super good. I mean, we're gonna allocate memory from the very beginning, right? Because we know we need something in the ballpark of 1,000 sprites, right? We want to shoot 1,000 bullets in the ballpark of 1,000 bullets. So we preemptively allocate this much data, so we don't have to copy stuff. If we run out of like locations in this list, we don't have to copy data from one location and RAM to the other and then allocate and then copy and then allocate again and so on and so forth. Like, this is really slow. Copying stuff is super slow. And so it's always whenever you're creating a list, it's really, really nice to just preemptively say, hey, dude, I would like you to allocate 100 elements for me from the very beginning. Okay, and that's how lists work. So that's your introduction to memory, RAM, how RAMs usually work, the decimal system, the hexadecimal system. When you create a variable, what happens? When you add something to the list, what happens, right? All of this is really, really important. And the fact that you now know that, you're a better programmer and you can program things a lot more efficiently. So now in here, right? So I want to show you this. I need to prove this to you, right? How do I prove this to you? Well, see the top 10 list? I said that you can check how many elements in the list when you do size. So when you check for the size, you know that there are 3 elements in here. But also in here, there's something called a capacity. A capacity is how much data you have reserved, or how many locations you have preemptively reserved. So what I'm going to do here, I'm only going to add one element. It's Final Fantasy. In fact, you know what? I'm not going to add anything at the very beginning. I'm going to say stdc out. I'm going to say count. So I need to figure out how many elements in my list there are, like how many elements I've added. And this is capacity. Capacity is the actual blocks I reserved. So this is how many elements are currently in, and this is how many reservations I've done. Okay, I haven't added anything to the list. Let's delete all this code. Just gonna delete literally everything. There's nothing here. Right? I've only created the list, and I'm just printing the count and the capacity, not doing anything else. So this should be 0, 0. I've added nothing, and the capacity should be nothing. 0, 0. You can see 0, 0. Let's add one element, one single element. I'm gonna do dot pushback Final Fantasy. And what I'm gonna do is that I'm gonna print that element also. So I'm gonna print the first element, what's inside it, and then I'm gonna print how many elements are inside and how many reservations we have. This is what I expect to happen. This will print Final Fantasy. This will print 1. And this should print 4. Let's press play. Well, I was wrong. Okay, so it said Final Fantasy. My count is 1, and my capacity is 1. Well, this is not good. What if I had one more element? Final Fantasy 2. And the second element here. Is this really just gonna have a capacity of 1? This is so stupid. Alright, so the standard library is that much worse than I thought. In C#, you actually do reserve you actually do have a reservation, extra reservation. But apparently here you don't even do any reservation. You just literally you go ahead and copy the data anytime you add new element. So this is much worse than I thought. All right, so it's much worse. How can we preemptively reserve some data? So what I can do here, I believe, is I can set the capacity here. If I'm not mistaken. I think I just do 10. Again, I'm a little bit rusty with C++, so let's see. Does this gonna give me capacity of 10? Okay, so this is, no, it didn't give me a capacity of 10. It actually, yeah, so not that. Okay, so forget that. So instead, what I'm gonna do is say dot resize 10. So the resize function, what it's it's gonna reserve 10 locations for me, right? It's not gonna add 10 elements. It's only gonna reserve 10 locations, right? So the count should be 2, and then the capacity should be 10, which is not the case at all. What the hell is going on? Am I wrong? Am I an idiot? I mean, that's possible. That's very possible. Let me put a breakpoint here. I didn't explain breakpoints. Yes, I'll explain them there. So this is actually allocated. This actually allocated. Okay. So actually the capacity is 15, even though I've only added 10. So C++ does do some optimization, but it's still allocate. It actually added 10 elements. I don't want you to add 10 elements. I want you to allocate 10 elements. It's a strong function. Capacity. Insert. Reserve. Is it reserve? Not resize. Yes, it's reserve. I'm so sorry. It's not resize. It's reserve. It's been a while. So now there's only 2 elements, but the capacity is 10. There you go. That's what I wanted to see. Okay, cool. So if I press play now, okay. So now look, the count is 2 because I only have 2 elements, but the capacity, the amount of memory we reserved is 10. So now we can add up to 10 elements before we run out, and we have to copy the data from one memory location to the other, right? So let's say I only reserve 5. You know what? Let's do 10. So I'm gonna add 10 of these. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I've added 10. Let's do just 9, right? So the count should say 9, and the capacity should still say 10, right? So I've added only 9 elements, right? The size is only 9, and the capacity is 10. I've reserved 10 locations, but I've actually only added 9 of them. Let's add the 10th element and see what happens. It should still be the same. It should say count is 10, and now capacity is 10. 10 and 10. Right? What if I add one more location? Well, if I add the 11th element, that means now we ran out of data. We ran out of capacity, right? Now we have to copy all of our memory, or all of our data. We have to copy all of our data into a new location in memory and reserve more stuff. I don't think it's going to reserve more stuff, does it? C++? It actually did. Okay, C++ is not that horrible. So you can see it reserved. I wasn't completely wrong. So it actually did reserve 4 more locations for me. So now, before the data is copied again, I have 4 more spaces. I can do 4 more pushbacks before my performance tanks and the data has to be copied to a new location in memory. Right? And so let's add 4 more. So 11, 12, 13, 14, 15. Let's do 16. So 12, 13, 14, 15, and 16. So now it should give me 4 more. So 16, 17, 18, 19, 20, 21, 22. This time give me 6 more locations. So I guess the implementation of this std vector is that it will add 2 more locations extra every time. So it'll start with 4, then it'll go to 6, then it'll go into 8, and so on and so forth. So it's reserved 22 locations, and out of those 22 locations, I've added 16 elements. Right? So hope that cleared up. And if you want to reserve, you can just reserve from here. What if I want to reserve 100? So now I allocate 100 elements, right? I reserve 100 elements, right? So I can add up to 100 elements. This count can go up to 100. I can push back up to 100. When I reach the 101 element, that's when my performance is gonna tank for a slight while I copy the data from one location to a new location, right? Until I go ahead, it will copy from one location to the other and reserve some more space. And we can do that easily if I put a loop here. So if I put a for loop and I say I want to do this 100 times. So I'm going to push Final Fantasy 100 times. Okay? And we reserve 100 times. So let's see how much capacity it's going to give us. Sorry, let's restart that. Alright, so we filled it now. The count is 100, capacity is 100. Let's add one more. So 101. We now are going to run out of capacity, reserved capacity. So what is the new capacity will be? 150. So now I've added 49 more. So we can allocate, we can push 49 more strings into this vector before we have to copy our entire data from one memory location to the other and reserve some even some more. So if I do 51, I add 51 elements. The capacity is now 225. So before our performance tanks, we have until 255. So rather than waiting for std vector to do this, I can just preemptively go ahead and just allocate data from the very start. I can reserve 1,000 locations. Right? So now I have 1,000 locations. So I can add as much data to this vector up until 1,000 locations. When I reach the 1001 location, I have to copy my data somewhere else. Right? I hope this made sense. I hope you understand the difference between count and capacity. Count is actually how many elements I have, how many elements I have actually physically added into the list. Capacity is just reserved. So I reserved 1,000 elements, and all of these 1,000 elements, there's no data. It's just empty data. I didn't assign any data yet. I didn't push anything yet. When I start pushing, then count will increase. But capacity is basically just, you know, how much I've reserved. So when you go to a restaurant and you reserve table for 5 and only 4 show up, that means you guys can have one more guest in the table join you before you have to change tables or add more chairs. So kind of the same concept. Right? Hope this made sense, and I hope this kind of shows you how lists works or how std vectors works, and how memory is handled, and how it is extremely important to know what's happening under the hood. Because if you didn't know this information, your performance would have been really, really bad. And so that's why kind of this is important to kind of know and understand, which is kind of cool, right? All right, so we talked about memory. We talked about hexadecimal, decimal, how lists works, how adding things to memory work. We added a skeleton that is renders some certain location. So next time, right? Next time we're actually gonna shoot our bullets. So we prepared for we learned about the std vector. Next time we're actually gonna use it in the actual game. All right. Hope you learned something. I hope all this made sense. I hope it's not too much information. As always, if you have literally any questions, please do let me know in the comment section. I'll go ahead and answer them. And if you could hit that like button and subscribe. Can't believe I'm saying that now. I used to make fun of YouTubers, be like, go hit the like button and subscribe. Now I'm saying that. So, yeah, could you please hit the like button and fucking subscribe? That'd be really nice. But yes. Alright, cool. See you guys. Take care.